these are some additional truss notes and concepts that you should be aware of that will help you. First of all, if you go to Wikipedia and just look at trusses, you'll get some good general information on trusses. If you go to truss bridge in Wikipedia, I'll share that with you. Truss bridge has got all different kinds of classic truss bridges. An Allen truss, a Bailey truss, a Baltimore truss, a bowstring truss with a curved top, a Brown truss, a Howe truss, all these different names kind of named after a person who popularized them. And so it's just interesting. It's interesting from a historical perspective, these different trusses. So you should look that up. Some more terminology with the truss. So typically a truss will have a top string of members and it'll have a bottom string of members. The top string is typically called the top chord. The bottom string, A, H, G, F, E, is called the bottom chord. If you're using a truss in a standard bridge configuration where there's a downward directed loading on it, the entire bridge is going to act like a beam and it's going to want to bend downward as it's loaded. If you bend that beam downward, then that basically puts the entire bottom chord in tension and it puts the entire top chord in compression. And then the individual members that go back and forth internal to it are often alternating tension and compression. So as we work examples, one of the things we're going to do is actually use our intuition to look for members that we are pretty sure are in compression, pretty sure are in tension, or even zero force members, which we'll talk about here in a little bit. And so if you're using your intuition, it helps you analyze a truss before you even start. If you have an overhanging truss like this, it's hanging from a wall and the truss just extends out like a cantilevered truss, and you hang a load from off of that guy, then that truss is going to bend downward under the action of that load. And so basically all of the top chord and DE are all going to be in tension. And this entire bottom chord is going to be in compression. And again, the internal guys are for the most part, probably going to alternate tension and compression, something like that. But learn to look for that. And so there's some questions on your test that will ask you, is this member in tension or compression? Well, you may be able to just tell by looking at it whether that guy's in tension or compression. Now, you may go ahead and analyze the truss, but if you've got two ways to get the same number or same answer, it helps you and it gives you a way to check what you're doing. Another thing about trusses, the trusses are usually composed of equal width sections called panels. Usually, sometimes there's non-equally spaced trusses. And at some point in an example, I might work for you some non-equally spaced trusses. But many times they're equally spaced. And so this is a 3-panel truss at 6-foot spacing. This is a 4-panel truss. And so when you're looking at the method of sections, you're basically going to be cutting the members, within one of these panels, for example. And if you learn the repeating pattern of a truss, and usually the angles are often repeating as well. So once you find the angles and the lengths and the repeating sections, it helps you with the geometry of the different successive pieces. Earlier, I said you should find the support reactions. Well, especially on an exam, you don't have much time. So first of all, the support actions are probably going to be given. If that's true, that's good. Another way to save effort is that if you're going to be using the method of sections where you cut this guy, and take the right-hand free body, then all you need to find is Fy. You don't need to find Ay, for example. And so if you just need one, find one. And like I mentioned earlier, if you have a truss that is cantilevered that extends out from a wall, and you're using the method of sections on this guy, if you cut him and take the right-hand free body, then you actually don't need the support reactions at all. You can just solve this right-hand piece without it. This is another trick. So if you are finding support reactions, and if the truss is divided up into equally spaced panels, and the loads are applied basically at equal spacing, then to find the support reactions, there's some tricks you can use. For example, if a truss has a single load in the middle, then what's AY? What's BY? Well, if we got one load in the middle, AY is going to carry half of the 100, BY is going to carry half, and so each of them is 50. You can write a moment equation to prove that, but basically you can tell by looking. What if you've got two loads that are equally spaced on a 3-panel truss? What percentage of this 100 is AY going to carry? And what percentage of the BY is BY going to carry? Well, you can tell by looking at it that BY is going to carry 2/3 of the 50 and 1/3 of the 100. AY is going to carry 2/3 of the 100 and 1/3 of the 50. Now you can write the moment equations and prove this, but again, because many trusses are vertically loaded with vertical support reactions, you can do this. Now, if there are non-vertical loads or non-vertical support reactions, you can't use this method, but this works for some trusses and makes it easier. If you have a 4-panel truss at 5-foot spacings, and you have a 100-pound load here, a 200-pound load here, and a 300-pound load here, then BY is going to carry 3/4 of the 300, half of the 200, and 1/4 of the 100. Again, makes your job easier. So these are just some tricks with trusses that help you with support reactions and help you identifying tension or compression like in the top chord or bottom chord.